Hey, this is Leach with Simpson Math, and today we're talking about irrational and imaginary roots in context of graphing polynomials. In this video, we will be taking a look at two examples, much more in depth than what we saw in the last video, so let's dive right in. So we have a function, f of x is 6x minus x cubed minus x to the fifth. So let's do our in behavior stuff. But you should notice right away that this function is not written in the correct order. Our terms are a little bit in the wrong order. So let me rewrite them and make my x to the fifth be first, then the x cubed, then the linear term. All right, that's better. Now I see that my leading coefficient is negative, so we'll be falling to the right, and I have an odd degree polynomial, so then we'll have opposite in behavior, and we'll be rising to the left. So falling to the right, rising to the left. And then since it's a fifth degree polynomial, I expect one less than that. That means 4 number of turns expected. So we could have as many of turns like this: 1 turn, 2 turns, 3 turns, 4 turns, and n going down. So it could have something like that. Now, remember, it's expected 4 turns. We could be done with this and actually have no turns and have something like that. We could end up with 2 turns or the full shebang with all 4 turns. Our y-intercept, well, our constant term is a big old plus 0, so our y-intercept is 0, 0. Since it's a fifth degree polynomial, we expect 5 roots. We have 5 roots. We know we're going to have 5 roots, but then we expect 5 x-intercepts. So our big task is going to be solving, how to solve for our roots. So what we're going to do first is we're going to set the function to be equal to 0. All right, so we let f of x equal 0, so that way when we solve and we find x, we're finding the x values that make the output, the y, be 0. So first we need to solve by factoring. So I'm going to find my GCF, which is this negative x, and factor it out. With the polynomial that's left inside is now, I have all the signs flipped, and all the number of x's have been reduced by 1. And one little thing to make my life be easier is I'm just going to divide everything by -1, which all that this does, since this is one big term, I'm going to divide everything by -1. If I divide by -1, 0 divided by -1 is just 0. And then all of this divided by -1 is now just that positive x. You could have divided by -1 at the very beginning and then just factored out the x, and you would have been left with here. So notice the values inside the parentheses did not change when it divided by that -1. All right. So now we need to then factor this x to the fourth. And you might be thinking to yourself, Mr. Leach, we've never factored an x to the fourth before. And you'd pretty much be right. So let's take a look at something called quadratic-like polynomials. If a polynomial is in the form a times x to the 2n plus b times x to the n plus c, where n is a natural number, or a natural number that says double bar n, that's a 1, 2, 3, 4, all the way up. Notice it does not include 0, does not include negative numbers. So starting at 1 and counting up, there are counting numbers. So n is a natural number, and then, so that means that if we have, if n was 1, then this would just be ax squared plus bx to the first, which we actually want to see, and then plus c. If n was 2, this would be ax to the fourth and bx squared. If n was 5, this would be ax to the 10th and bx to the 5th, and then c technically times x to the 0 power. All of these have a secret implied x to the 0. All right, so you should notice the relationship between these exponents here. And then depending on the coefficients a, b, and c, so not for all a, b, and c's, but for certain a, b's, and c's, then the polynomial can be factored just like a quadratic. That's why we call these quadratic-like polynomials. Another way of looking at it is this. So here's the polynomial that we're left with after we factor out that GCF. And I can force this to sort of feel quadratic. So I could rewrite x to the fourth as a square, like this, x squared squared. And then I could rewrite this x squared term as a kind of like a variable or variable just in the form of this base variable, and it's this with just this x squared and then minus 6. So notice we have our squared, our first power, and then our secant to the 0. So this is a quadratic like polynomial. So like I said, we can just factor this like using the AC method. So a is 1, c is -6. So a times c is -6, but multiplies to be -6 and adds to be +1. Well, that's this -2 and +3. So then we can do our AC method. So I can rewrite this x squared as a -2x squared plus 3x squared, and then do our factor by grouping of this part. So what's the GCF of the first two? That's x squared. What's the GCF of the second two? Well, that's a +3. Make sure we have that +3 there. Notice inside each of these, we are left with an x squared minus 2. So I can factor that out. Here's our x squared minus 2. And left inside is our x squared plus 3. All right. So here we factor this. We have this factor x squared minus 2, which actually can be factored, as we'll see in a minute, but we can actually just pick up and solve from here. And then x squared plus 3. So let's set each of these factors equal to 0 and solve. So we'll first up set x equal to 0. And so, that's it. Set x equal to 0. Ta-da, you're done. X is 0, and we get an ordered pair 0, 0 for that x-intercept. Then I can set x squared minus 2 to be equal to 0. So x squared minus 2, then we add the 2 over, and then we square root both sides, not forgetting our plus or minus. So now we have a negative square root of 2, 0 for one ordered pair, and a square root of 2, 0 for the second ordered pair. So you see here, we have two irrational roots from this. So from this factor alone, we have two irrational roots. And now for the x squared plus 3. Take the x squared plus 3, set it equal to 0. Subtract the 3 over. We did this on the last video. And when I square root a -3, we end up with a plus or minus I times square root of 3. So we have no x-intercepts from these two imaginary roots, but they are 2 of our 5 roots. So we do have our 5 roots. We have 2 roots here, they're imaginary, 2 irrational roots, and 1 real root that's an integer. So that means I have 3 x-intercepts. I have an x-intercept of -2, 0, 0, 0, and 2, 0. An important observation, and this is going to be helpful for our next lecture, is that f of x can be rewritten as a product of linear factors. I can take each of my roots, and with each of these 5 roots, set them to be x minus the root. So x minus 0 is just x. X minus positive square root of 2 is x minus square root of 2. X minus the negative square root of 2 is x plus square root of 2. And then I can do the same things with these two imaginary roots, x minus I square root of 3, and x minus a negative I square root of 3, which is x plus I square root of 3. And then I also have our leading negative out front here as well. So this polynomial down here doesn't look like one, but these 5 linear factors all multiplied together is the same thing as f of x. If I was to FOIL this together, if I was to take these two and FOIL them together, and take these two and FOIL them together, I would get their counterparts up here. So this is the difference of two squares, where we force this 2, because if I was to square root 2, I get, square root of 2. And I don't have a thing called the sum of two squares that gives me factors, because the only way you do that is if you have imaginary numbers. But if you would have forced those factors and allowing imaginary numbers, it would be like this and has that feel of the difference of two squares. So this is important to note that I have a 5th degree polynomial, and I can rewrite it as a product of 5 linear factors. So before we start graphing it, we need to look at a few things. First, we need to approximate square root of 2. So square root of 2 is approximately 1.4. I can get this by knowing that square root of 2 is a little bit more than 1, but less than 2. And the square root of 2 is popular enough, you should know that it's at least 1.4. So then positive square root of 4, so positive square root of 2 is 1.4 about, and negative square root of 2 is about negative 1.4. There's a lot of things going on with this particular polynomial, so just want you to be mindful that there are things that affect our turns and the number of turns and where they turn. So it might not be perfectly obvious with what we've looked up so far, but my expectation is that you graph these things that I've taught you. The leading term test and in behavior, y-intercepts, x-intercepts, make sure that these are the real roots. You deal with multiplicity, and then sketch a function that puts all those things together. There might be several answers that may work, and so let's actually look at this particular function to see what I'm talking about. So if I was to graph this, well, I lead off with my x-intercepts, 0, 0, my square root of 2, 0, and negative square root of 2, 0. 0, 0 is also my y-intercept. I'm falling to the right and rising to the left. And so I can put all that together, and at minimum, I start high, pass through this negative square root of 2, 0, have to turn around and go through my y-intercept and x-intercept of 0, 0, turn around, and then go through square root of 2, 0, and then on down. So that's actually what the function does look like, but notice that's only 2 turns. In a 5th degree polynomial, it is possible that you have additional turns. All right, I have highlighted here in orange and highlighted here in purple these sketches of some potential extra turns that you might see. And when you see these extra turns their turns aren't crossing over the x-axis, that's an indication of imaginary roots at play. So sometimes they're there, sometimes they're not when they're imaginary roots. In this case, it's actually not. And there's something that you that we've talked about previously called even and odd functions, where here this says that we actually know that this particular function would have had this shape, because if you notice, it's symmetric about the origin. If I was to take this function and spin it at 180 degrees, it would be the same thing. This is what we call an odd function. So if I was to graph this using Desmos, this is what it looks like. I don't have these extra turns. That's why we say we expect 4 turns or 2 turns, because we might not always get them. So there's this property about odd functions. It says that f of negative x is equal to a negative f of x. So if I take negative x and plug it into my function and simplify, notice what happens. A negative x to the 5th is, well, a negative x to the 5th. So I get a negative times a negative, and that's x to the 5th. Same thing with x cubed. And then a positive 6 times a negative x is a negative 6x. So notice, this is the exact same thing as just multiplying my original function times a negative 1. So this is what we call an odd function. And then just a reminder that an even function is if I plug in a negative x, what comes out is actually just my original function. It actually doesn't change anything, and that's when it's symmetric about the y-axis. All right, so this is our graphing this 5th degree polynomial, where we have had 2 imaginary roots and 2 irrational roots. Let's take a look at a parabola. So we have g of x is 2x squared plus 8x plus 7. Now, since we're taking a look at a quadratic, I would like to remind us about the relationship between the number of roots and what's possible with a quadratic. We could have 2 real roots and 2 x-intercepts. If you recall with the quadratic formula, that's when our discriminant is positive. So notice we have this parabola that crosses twice, and it would work whether it's going up or going down. I could have 2 real roots, but only 1 x-intercept. We get only 1 x-intercept because it's what's considered a double root. There's 2 roots that basically come together, and they are on top of each other, and we have just 1 x-intercept. And this is when it touches and turns, but we have that multiplicity, and it works either way. We could also have 2 non-real roots, which would mean that we have 0 x-intercepts. So we have a parabola that does not cross the x-intercepts, the x-axis at all, and it works either way. So Keep this in mind when you are working about quadratics. You can have 2 real roots and 2 x-intercepts, 2 real roots and only 1 x-intercept, or 2 non-real roots, which would then be 0 x-intercepts. So back to this function. I can then do our in behavior stuff. And I know that it's going to be rising to the right and to the left because we have a leading coefficient of a positive 2. And it's an even degree. It's a quadratic, so it's then also going to be rising to the left. We have our y-intercept of 0, 7. And we know we're going to have 2 roots. And we're expecting 2 x-intercepts. But as we just talked about, we might not get those 2 x-intercepts. Might be 1, might be none. All right, so now we need to set g of x to be equal to 0. And then let's solve. But we should be quick to notice that this does not factor, or at least not factor nicely. So g of x has an AC of 14. If I do 1 and 14, I get 15. And 2 and 7, I get 9. And I need 8. So that's not going to happen. We're not going to get 8. This is not going to factor nicely. So that means we need to use the quadratic formula. So let's plug in a, b, and c, and we get this. And as you know, I like to do my discriminant work to the side. Here's my discriminant written down. If I square 8, I get 64. And then 4 times 2 is a negative 8. Negative 8 times 7 is this negative 56. Add those up and we get 8. And so I can rewrite 8 to be 4 times 2, where 4 is a perfect square root, which is square root is 2. So we end up with 2 square root of 2 is my the work that I get out of my discriminant when I square root it. So let me copy that back over. And I end up with negative 8 plus or minus 2 square root of 2 over 4. I'm going to, fancy word is decompose the fraction or just break it apart. And so I get negative 8/4 is negative 2. And 2 over square root of 2 square root of 2 over 4. I can reduce the 2's here and left with just square root of 2 over 2. So we actually have 2 roots, or 2 x-intercepts at negative 2 minus square root of 2 over 2, and negative 2 plus square root of 2 over 2. I have those negative 2's highlighted because let me go ahead and talk about that. That is our axis of symmetry. Our axis of symmetry is x equals 2. Recall that the axis of symmetry formula is x equals negative b over 2a. Our formula for the quadratic formula has this negative b over 2a right there. It is literally the axis of symmetry plus or minus the distance from the axis of symmetry to my roots, to my x-intercepts, if they're real. So that's what this is. This is my axis of symmetry plus or minus square root of 2 over 2, which is the distance from my axis of symmetry to my roots. So let's talk about actually finding that in case we need to graph it, because we will in a second. So just a mental estimation. You should know that square root of 2 is 1.4. We talked about that just a second ago. If you don't, just think about this. Square root of 1 is 1, square root of 4 is 2, and square root of 2 is tucked in between those. So that's where we get it at. That is about 1.4. So then square root of 2 over 2 is approximately, well, let's just sub in that about 1.4. So 1.4 over 2. So square root of 2 over 2 is about 0.7. So I can use that 0.7 as a distance from my 2. So let's go ahead and see this on the graph. All right, so before we look at where we get the vertex and all the things, let's just check about this axis of symmetry and these points. So here's my axis of symmetry at x equals negative 2. And then if I add square root of 2 over 2, or about 0.7, I get here. And that's this x-intercept, negative 2 plus square root of 2 over 2. And if I go back to negative 2, and then I subtract square root of 2 over 2, or subtract about 0.7, and then I get about here. So that's how I can find my 2 roots. All right, so let's check about how we get my vertex and the other points. So for my vertex, we plug in this negative 2, because my vertex lies on the axis of symmetry. Take the negative 2 and plug it in. And we end up with g of negative 2 is negative 1. Be mindful that you square before you do your multiplication. So that's how we get our vertex of negative 2, negative 1. All right? When we graph, We then we can graph our y-intercept at the 0, 7. And then notice that this is 2 units away. So I can do 2 units away on the other side to get the symmetric point, which is negative 4, comma 7. Also notice that this is left 2, up 8. And we know that that should make sense because this is a parabola that's been stretched vertically by a factor of 2. So then that's why it makes sense to do 2, 8. There's also another dot at 1, 2, just in case if you wanted to know another nice dot. So I can label my symmetric point to be negative 4, comma 7. And then lastly, my domain and range. Domain is negative infinity to positive infinity, and my range is from negative 1 to infinity. All right, make sure that we label all the points. It's important that we do that. So I have all these little parts labeled. I've labeled my axis symmetry, labeled my vertex, labeled my x-intercepts, my y-intercept, my symmetric point, and also said that this function is g of x. You don't have to label these arrows. That's just sort of kind of to help keep me straight the first time I graphed that. All right. So in today's lecture, hopefully you saw how we can graph polynomials when we have irrational and imaginary roots. Hope this helped you understand this a little bit better and can do your homework a bit better. Let me know if you have any questions, and I'll see you next time.